Hello everyone. This is Yue from the University of Correlated in Australia. Today I will present the paper Runtime Analysis, Random Local Search, and the 1+1 EA for the trans-constant knapsack problem with correlated uniform weight. In the beginning, I want to warn this because this one is the technical paper, so it contains so many proof, and due to the time limitations, I'm not allowed to go into detail for those theorem. So if you are interested, please, I highly recommend you to read the paper. And the problem we discuss in this paper is the trans-constant knapsack problem with correlated uniform weight. It is a version of stochastic knapsack problem, in which the knapsack problem is a best-known combinatorial optimization problem. Till now, the trans-constant knapsack problem has been studied in several papers and also has theoretically discussed in detail. However, consider this problem with the setting of correlated uniform weight is new, and it makes the problem more related to a real-world application. The techniques that are used in runtime analysis have significantly increased understanding of bio-inspired approaches from a theoretical perspective. As beginning of this analysis, we investigated the simplest heuristic approach, named random local search and 1+1 EA. Moreover, we investigate two settings of the problem and proved time bounds for both algorithms. Here's the outline of today's presentation. First of all, I will introduce the setting of the problems. Because we assume that weight of items are correlated uniform, so we separate the items into k different groups, and there are m items in each group. And given capacity of the knapsack, we assume the items in different groups are independent to each other, but items from the same group are correlated with a shared covariance. The Eij denotes the jth item in ith group, which has corresponding non-negative stochastic weight, expectation weight, variance of weight, and profit. Note here, in this paper, we assume the covariance of all items are all equal to D. Here is the model of the problem, which aims to maximize the profit of all selected item and subject to the chance constraint. The alpha is a given threshold of the probability. The solution of the problems is a vector of binary variables. Each binary variable decide to select these items or not. And then we also can calculate the weight, expectation of weight, variance of weight of every solutions. And here, the variance is the sum of the variance of selected item and the covariance of the selected items. So in this problem, we defined two special type of solutions because it's more complexity. So we'll give a simple example. For example, in this case, there are 3 groups and 4 items in each group. Then, among all solutions with exactly 6 1-bits, we say this type of solution named balanced solution, which select exactly 2 items from different groups. So, which means it selects equally number of items from different groups. And then we say the solutions which select the full number of items in one group, any group, and select the least 2 items from another group, named the most unbalanced solution. Then, in general, among all solutions with exactly L1 bits, we can define the number of selected items from the deterministic number of groups for these 2 different types of solutions. And we also can calculate the covariance of these 2 types of solutions. Here, we present the surrogate functions of the chance constraints. And we use this quality to express the variance of each solution with exactly L bits. In this paper, we studied the Chebyshev inequality, which can be used to calculate the upper bound of the chance constraints. Then, applying the Chebyshev inequality, we can have the surrogate functions denoted by beta of x. And we can have the upper bound of the covariance of any solution with exactly L1 bits. The f of x is the Phoenix functions of this problem, which can be used in any heuristic approach. And according to the Phoenix functions, there are two types of infeasible solution. The first type is the solutions which has the expected weight greater than the capacity. The second type of infeasible solutions are the solutions whose probability of violating the chance constraints is greater than the given threshold alpha. In this paper, we studied two algorithms. The first one is random local search, and second one is 1+1 EA. So in the beginning, we analyzed the expected steps of both algorithm needs to obtain a first feasible solutions. We start by the random local search. The proof idea is because we know adding new items to any infeasible solutions will increase both, no matter it's an infeasible solution or feasible solutions, will both increase the expected weight and the variance of weight. So according to the Phoenix functions, before the algorithm find first feasible solution, it will never accept any mutation step which increase the number of selected items, which indicates it only accepts a single one bit flip, which flip 1 to 0 or flip 2 1 to 2 0. Then we can have the upper bound. Then we discuss the 1+1 EA. The proof idea is similarly to avoid the first type of infeasible solution for 1+1 EA. Before it finding a solution whose expected weight is less than the capacity, it will never accept any solution which increases the number of selected items. So before producing such items, the considered problem can be treated as 1 max, and we can have the time bound for the 1 max problems. Then, after finding such solutions, the algorithm always accepts a solution with smaller beta of value, which is the probability of violating the chance constraint. Then we define the potential functions, which is h of x is the sum of variance and the covariance of a solution. And according to this h of x, we want to define, we assume starting by the x, the possible offspring which have exactly L1 minus 1 bit have this relationship. Then we assume the next possible accepted solution with exactly L1 bits should match this relationship. And we only consider 1 bit flip mutations for the 1+1 EA here. So we set R1 to Rk are the number of selected items from each groups. And the x prime is generated by flipping 1 bit from the group I. So the reduction of potential should calculate by this. Then because there are Ri items in these groups, so the total contribution of this group can be calculated by this function, which greater than the real reduction of potential for this group. Then summing all groups, we have these functions, which given an upper bound of the potential function. Then by the multiplication drift analysis, we can have the upper bound. We can have the upper bound of the expected time to reach out a solution with this L1 bits. Because there are at most n1 bits in the current solution x, so the expected time is bounded by n square log n. Now we start to analyze two different settings of the problems. First one is we assume all the profit of items are all equal to 1. Then we define the potential search space like this. The solution in each level are all feasible and have the same number of selected items. And we also define two parts of each potential. The first one collects solutions which are not able to add in another item. And the second type collects solutions which can add at least one more item without violating constraints. Then we start by analyze the random local search. We say the expected time until random local search find the optimal solution is bounded by NQ. The proof idea is because we know that the balanced solution in each level is the solution with the smallest covariance. So we want to prove that the expected reduction of the covariance by changing a solution from current solution to the balanced solution. So the S of X is the number of items belong to any balanced solution but not belong to the X, and the T of X is the number of items belong to X but not for any balanced solutions. So we assume G is equal to S of X equal to T of X. Then we know that most G1 bits of X can be swapped to any 0 bits. And the probability of such a swap is calculated by this one. So the expected time the random local search need until it reaching to G equal to 0 is bounded by this. Then we have the final time bound. So we have to be quicker. Then we analyze the 1 plus 1 EA. Similar to the 1 plus 1 EA, similar to the random local search, we assume the solution X is belong to the potential part which cannot add in another items. Then to compare to any balanced solutions, we can calculate the total contribution by flipping items belong to the X, not belong to the balanced solutions, and also flipping those 1 to 0, the total contributions is like this. And then we also can calculate the contributions by flipping the 0 in X, but should be 1 in any balanced solutions. It's like these functions. Then summing them up, we have the total contributions by producing this two-bit flip, swapping from X to a balanced case. Then we have these functions. So because the probability of such a swap is like this, then the expected one-step changing is these functions. Then if we're already producing a balanced solution in each levels, the 1 plus 1 EA will only accept the offspring with more 1 bits, and then we have the final improvement to calculate the upper bound of time bound. Now we discuss the second setting of instance. In this type of case, the profit in each groups are different. They are arbitrary, and the profit profile are similar in different groups. Like this definitions. So for the random local search, the expected time until it produces an optimal solution is bounded by NQ. So the proof idea is similar. We sort all the items according to their profit without considering the profit, and we call a profit profile PJ, means the solution X select all the items from I to J according to this sorting, and without selecting the item J plus 1. So the next accepted solutions generated by X must contain the same profit profile. So without changing the number of items, transfer solution X to another solution x prime, which contain the profit profile pj plus 1, is time bounded by n square because it will only accept 2-bit flip. Then, because there are at most n items, so the expected step is n2. Then for the 1 plus 1 EA, let's speed up. For any current solutions, we should prove after this time-bound step, the optimal solution, either the optimal solution have been found or a solution which have greater, whose profit is greater than any solution in current level has been produced. So we assume we set this x max is the solution which have the possible maximal profit in this level. And we define the loss of the x and the surplus of the x. Summing them up, we have the R is the number of items belong to x max, but not belong to x. So after swapping this R 2-bit flip, we can increase the profit. So this increase in profit is calculated by comparing the profit of solution X and the profit of X max. So we have these two functions because we're sorting all the number of elements chosen by X in group. So then we have these functions because the X max should be the balanced solutions which have the lowest probability. So we have these two sortings and we have these two relationship. Then we have this relationship means the number belong to the X is this than the X, the sorting, but it's complexity. Please read paper, please. So in the end, but after those swapping, we can calculate the upper bound of the reduction with the increase of the profit. So the expected increase in profit is at least like this. Then for any non-maximum solutions, by applying the multi-captive drift analysis before producing such a solutions, it needs at most these steps because then since it have at most n levels, there we can calculate the final upper bound of this time bound. So the conclusions, we discussed the chance constraint knapsack problems with the correlated weights. It considered the dependent stochastic variables and its more relatives in real-world problems. And then we carry out theoretical analysis on the expected optimization time of random local search and 1 plus 1 EA for the problems. And then we prove bounds for both algorithms and consider two settings of the problems. Our proofs are designed to prove insight into structure of the problem and to reveal new challenges in the runtime analysis of the problem. I really apologize if I'm not explaining any details, but we have time limitations for the presentation. So please, if you are interested, feel free to contact me or read the paper.